Hi, this is Sangeeta from ESB Engineering College, Karur. Under the lecture series of prefabricated structures, now we will be seeing related to design for abnormal loads, and the subtopics are how the progressive collapse will occur, and what are the codal provisions available for progressive collapse, and equivalent design loads for considering abnormal effects, and the importance of avoidance of progressive collapse, and the case study relevant to the progressive collapse. The normal loads acting on a structure is shown in the figure, and also the abnormal loads acting on the structure is shown in the figure. And the nature of the normal load is always be static, and it will be continuous, and it will be calculative in nature, whereas in abnormal loads we cannot predict the time at which it will occur. It is dynamic and instantaneous, and it calls the chaotic experience. And the material state here, it behaves in an elastic range in case of normal loads, whereas in case of abnormal loads it results in plastic hinge formation and high ductility. And the precast challenge is maintaining geometric stability when abnormal loads are acting on the structure, and defining the threat, that is progressive collapse. It is a structural failure initiated by localized damage that triggers a chain reaction, resulting in the collapse of a disproportionately large part of the structure relative to the initial cause. And in progressive collapse, the structure's redistribution mechanism fails, turning local yielding into a global catastrophe. And the standard failure rule is damage is confined to the impact zone. But in case of progressive collapse, the damage will first occur as a localized in nature, but within a fraction of second, it will cause the entire structure to be collapsed. And the mechanism of failure, that is the domino effect. First one is local trigger, which damages only the particular portion of the entire building. That is, for example, here an abnormal event instantly removes a primary vertical load bearing member, that is a column. And kinematic shock, supported elements experiences sudden free fall, generating massive dynamic impact forces. And the next one is redistribution failure, when the load distribution is not proper. That is, the connections lack tensile capacity to bridge the gap, and the forces cannot bypass the void. And first one, member insufficient capacity to withhold the load, and in such case the adjacent column will fail, and the entire section will fail. And the precast vulnerability, a system of discrete elements. As we all know, prefabrication is the system of separate elements joined together at the particular site with the help of joints, connections, and sealants. In cast situ concrete naturally possesses structural continuity and robust multidimensional load parts, whereas in prefabrication, structures act as giant assemblies of discrete parts. Joints are the absolute part of the weakest links during abnormal loads, and connections are often displaced and designed purely for bearing and lack of continuous tensile reinforcement. Resilience in precast structures must be explicitly engineered into the connections so that the vulnerable actions can be avoided. And equivalent design loads. The dynamic kinetic energy can be through codal provisions, that is smoothing and dampening. It will convert into static equivalent lateral forces. We cannot perfectly predict or calculate the true dynamic time history response of a building to every possible earthquake or cyclone. We cannot predict, since it is, as the name indicates, it is abnormal and it is instantaneous and dynamic. So we cannot predict, But based on some codal provisions and dampers and some other materials, we can reduce the effect of the progressive collapse. The equivalent static force method, we translate dynamic chaotic energy into a set of codal smoothing and damping, that is equivalent static lateral forces. If the structure can withstand those, that is the horizontal arrows, it possesses the required stiffness and strength to withstand the dynamic effect. Lateral threats, seismic versus wind effects. As we all know, the two major lateral forces acting on a component or a building will be wind effects and earthquakes. So the source of earthquakes is ground acceleration, and the mechanism involved is force is equal to mass into acceleration. Heaviness is a disadvantage. Target attacks the centers of mass. Target stiffest structural elements. Precast focuses to energy dissipation, ductile point detailing, and diaphragm actions. In case of cyclones, that is aerodynamic forces, the sources are from extreme wind pressure and suction, and the mechanism, the force is directly proportional to the square root of the velocity and the exposed area. The target, it attacks the building envelope, targets the wall panels and exterior connections. The precast focus is to uplift resistance, secure panel corrections, avoiding aerodynamic resonance. The codal provisions which mandates the structural survival are ductility detailing, which is very essential and mandatory, social confinement reinforcement in boundary elements to ensure they can bend without breaking. That is plastic rotation capacity. In the figure, it is clearly shown that special confinement reinforcement in case of ductile detailing helps for the reinforcement to bend without breaking, and the structural codal provisions will help you to reduce the effects such as horizontal ties, it is described in this image, and the vertical ties, stirrups. They provide minimum tensile forces that horizontal and vertical ties must withstand, ensuring the building holds together. And element removal analysis. Analytical proof is that if one nominal load bearing element is removed, the remaining structure maintains the equilibrium. For example, if one particular component, so for example beam or a column, is removed due to some unavoidable effects, the remaining structures to withstand and carry out the purpose for which it is defined. So in such a way, we have to design a structure so that it will not get into progressive collapse. International codes, for example, American Code of Concrete Institute, Europe Code, enforces these provisions to transition precast designs from bearing only to one component to the entire structure. The next, the critical importance of avoidance of progressive collapse. Why does it goes beyond the math? Because life safety, which is the prime directive, the abnormal loads occur without warning. Avoidance mechanisms do not guarantee an undamaged building. They provide the crucial time required for the human evacuation before global collapse. The next one is disproportionate economic loss. For example, if losing a single column due to a blast is cost thousands, but losing the entire building due to a blast and due to the lack of interconnected ties cost millions and triggers total assets writes off. And public trust in prefabrication. The public should have an interest in prefabrication, and they should know these disadvantages and how it can be rectified before designing a structure. That is, the major disadvantages in prefabrication is joints and connections, and the next one is occurrence of a progressive collapse. It should be designed in such a way that it is not occurring at an instant of time, giving a minimum amount of time for the evacuation of men and materials. The case study regarding progressive collapse is the Ronan Point, which is happened in the year 1968. The event is a minor gas explosion in the kitchen on the 18th floor of an entirely precast large panel concrete building. The trigger, the internal blast pressure blew out the exterior load-bearing wall panels of that specific apartments. The result, the loss of the support caused the floor slabs about to collapse. Their kinetic impact triggered a vertical chain reaction, destroying the entire corner of the 22-story building down to the ground. The legacy, a single catalyst for modern progressive collapse engineering and the global mandating of ties forces in precast codal provisions. So from this case study, we can know that there should be n number of and appropriate number of ties available, so that losing a single column or a beam or a specific component would not damage the entire building. In this case, a gas explosion in a small 18th floor of one apartment causes the entire side of the building to get collapse. And while analyzing the failure, what went wrong, it came to know that no alternate load parts. When the 18th floor wall vanished, the structure had no framing mechanism to bridge the span. The upper loads had nowhere else to travel but straight down. And the next one is gravity only connections. These joints relied entirely on friction and gravity. There were absolutely no continuous vertical or horizontal steel lights physically bolting the panels together, and the lack of catenary action, that is, the floor slabs were incapable of acting as a continuous suspended membrane. Once the primary supports were removed, they fell instantly as discrete heavy concrete blocks. So this shows the precast concrete floor slab, and this is narrow unreinforced ledge, and the orange color indicates the missing tensile tie. The three prerequisites of progressive collapse avoidance. First one is indirect design. Tie forces, providing continuous interconnected networks of steel reinforcement throughout the precast assembly to physically bind the discrete parts together like a three-dimensional net. Direct design, alternate load parts, engineering the structural framework so that if primary load-bearing element is fails or removed, forces automatically bridge the resulting void and safety transfer to the adjacent members. And next one, specific local resistance, designing key structural elements and corner elements, blast explosions with extreme shear and flexible connections so that they can withstand the load without failing in that localized area. And implementing the net, the types of structural ties. There are different types of ties. They are internal ties, peripheral ties, vertical ties, and horizontal ties. Internal ties, in the image, which one is marked in blue color, anchor floor elements together, allowing the flow system to act as a unified diaphragm or suspended via catenary action. And peripheral ties, these continuous reinforcement acts as a structural belt around the perimeter, preventing the building from bursting outwards. And vertical ties, these continuous columns of steel running from foundation to roof, preventing the uplifting or free fall of stacked wall panels. Horizontal ties, which is given as discontinuous lines according to the lateral load resisting frame, that is walls or columns to the floor. Shear forces are transferred through these ties. And engineering redundancy, which is the alternate load parts, the bridging concept. The building is designed to physically bridge over a localized failure in a real time. Requirements for success. Flexural capacity. The beams directly above the void must suddenly double their span length and resist massive unexpected bending moments. And shear capacity. The connections must possess extreme shear friction to withstand the intense lateral reduction of gravity loads. And next one is joint ductility. These connections must be detailed to show or allow plastic hinge rotation, absorbing the kinetic energy without brittle failure. And the resilience grid, the ultimate precast philosophy. Designing for abnormal loads is not only about preventing the damage entirely, but it is about controlling the geometry of failures by integrating the rigorous codal provisions and comprehensive multidirectional tie networks and calculated equivalent design loads. We transform isolated fragile precast components into an indestructible interconnected network. So the result is as a structure that bends, bridges and redistributes ultimately survive. So with this we can end this lecture sessions. Thank you for watching.